This morning's presentation is all about energy efficient cooling at no extra cost. My name is Peter Thomsen. I'm from Armstrong Fluid Technologies. I'm a director there of the Building System Solutions Group, a global director. And our mantra at Armstrong over the past 20 years has been all about lowest first installed cost and lowest life cycle operating costs. And the way that we've achieved that and made it a reality is factory integration and the creation of intelligent devices. So that's what we've leveraged here today and in the past 15 years in the data center community, and that's what I'm going to be talking about this morning. A little bit of background on Armstrong Fluid Technology. We're a designer and manufacturer of heat transfer and fluid flow equipment, systems, and technology. My background, I've been with Armstrong since 2001. I started my career in the nuclear industry as a junior engineer and progressed through transit industry and then into heavy industries like mining and pulp and paper, and then eventually at Armstrong, where we service a number of different industries, including data centers for the past 20 years and telecommunications, comfort cooling in commercial buildings, light industrial applications, and other issues around the world that involve heat transfer and fluid flow. Just connecting two dots there, what I'm showing here is a rapid deployment scheme that's implemented by a lot of our data center clients, and that has to do with a modular cooling unit that's being set by that crane on the top of this data center. And we deploy approximately 500 of those a year around the world. Contains heat exchangers, maybe a chiller inside of it, pumps, control devices, automation solution, power distribution, the full gambit, basically a mini mechanical room on a rooftop. And if we look at that little box there and we look at that deployment on that data center, approximately 10 to 15 of those, depending on the size of them, is roughly the same power generating capacity as one nuclear plant. So the implications of what we do here in the data center community and telecommunications in terms of the efficiency of our basic processors and how we cool them and how we get the motive power into those sites is very important for us as a global initiative when we talk about our carbon footprint. Armstrong has a mandate through our sites that we deliver to reduce the carbon footprint of the world by 2 million tons by the year 2022. So enough introduction. I've talked a little bit about Armstrong's products and solutions being heat transfer and fluid flow, and there are a lot of people in this space, but what we've done is we've entertained two new core competencies and integrated those into our product solutions that enable us to do some fantastic new things. The first is demand-based control, which is a methodology of feed-forward control, and I'm going to define that in a few seconds, and also digitalization, making real-time digital performance maps of not only our equipment, but also the installation that they go into and the full application that they're deployed into. So the way I'm going to proceed this morning, I'm going to talk a little bit about feed-forward control. There may be some people in the audience who don't know the difference between feed-forward and feedback. Talk about predictive model and the implication of using predictive models for maintenance, condition-based maintenance and operating availability. Talk about sophisticated digital twins using cloud-based analytics. Talk about a new machine learning method that we've implemented on our cooling plants, and what the implications are for designers today when you're designing your cooling systems and the world of 2N, N+1, and what redundancy really means when you have real-time capacity calculation for part load applications. So starting fundamentally at the beginning, for the last 800 to 900 years, feedback control loops have been employed around the world on some of the simplest systems, and if there were a thermostat in this room today, that would be a very good example where there's a set point of maybe 23 degrees for comfort, And if this reading goes above that set point, there's a controller that says there's an error. I'm either above or below that set point, and I need to do something. I need to speed up a fan. I need to open a chilled water control valve, let more chilled water into the space to help keep the people in the space comfortable. So that's a feedback control loop. It's not directly analyzing the process that's being controlled, but it tends to work. There's a little bit of hunting and drift that occurs over time, and we've learned how to tune that so that we minimize that hunting and that error as it tries to hit set point. So let's talk about feed-forward control. This is the more important thing to understand, and if we employed feed-forward control in this space, we would be able to count the number of people, know that for your size and your weight, how many calories of heat energy you're releasing into the space, how many lights are in the space and how much power those lights are putting into the space, and all the other sources of heat. We'd say we need to apply 200 kilowatts of cooling to that space. So what's the best way for us to do that? And there's a map, a predetermined map of how fast the fan should be spinning. There's a map that says what the control valve setting should be, and there's a map that tells us what the chilled water supply temperature setting should be. And the feed-forward control will say, okay, for the load of 200 kilowatts of cooling, there are my set points, I just go there. So there's no hunting, it's a direct control, feed-forward method, a predictable outcome. And if perhaps we're not able to achieve our temperature set point with that arrangement, we've learned that something has happened. Maybe the coil has a clogged air filter and it's a hard time getting enough air. We can adapt and we can learn that the condition of that equipment has changed and we want to change our control map, and that's a little bit of the learning process. So very difficult to do learning, machine learning with feedback control loops. Very easy to do machine learning with feed-forward control loops, where you have a predictive outcome from your original model. And that's what we've done with our automation systems. We've used feed-forward control, and as a simple example of how that gets deployed, I'm going to use a product in a two-dimensional space. It's not because we manufacture pumps, it's just because a pump really is a two-dimensional space. And what we've done with our hydraulics and our pumps, we've designed them so that for the amount of flow going through the pump and the amount of pressure across the suction and the discharge of the pump, there's a unique combination. We call that head and flow for these two dimensions, a unique combination of head flow and pump power and speed. So with an intelligent pump where we have the power supply coming into the pump and it has its power converter, its frequency converter, its motor, and all that gets mapped in the factory, when we are operating the pump at a certain power and speed, we also know the head and flow. So now we've created essentially a flow meter out of our pump or a pressure sensor out of our pump because it has that intelligence through that mapping. So how do we do feed-forward control with a device like that? So traditionally, on a cooling coil in a system, as the load goes up, there's a requirement for more chilled water flow through that coil, and it's regulated by a valve. So valves regulate flow, and the pump generates head pressure. What we want to do as that valve opens is we want to generate more head pressure to give that valve the best of valve authority possible for that operating load. So as the flow goes up, there's also more head or pressure loss in the piping system, so we need to generate more head pressure at the pump to accommodate. So this would be our feed-forward control map for that pump. So if we're starting at the green point, that specific load point, and as the cooling system starts to load up, the valve will open and it will draw more flow. Even as the pump stays at its original speed, the flow will increase through that pump. We'll see the power go up on the pump. It's related to flow. And we'll see that we're off our control curve. So what the intelligent pump will do, it says, I need to get back to that blue control curve, and I will increase my speed to get back on that control curve that's been mapped in my controller by increasing speed and increasing the head pressure. giving the valve its proper authority, giving enough flow, enabling enough head pressure for the flow within the system to satisfy the load at that point of the day. So that's just the beginning. What we do beyond that, we can also integrate vibration. So with an accelerometer embedded in this device, and this can be done on any mechanical rotating device, we can integrate vibration, and we can learn things about the device itself if it has some damage on it, and we can learn about the environment around it, like the strainer upstream maybe is clogged and causing cavitation. So a lot can be learned by combining vibration information with power, speed, flow, and head. And then you can take it to the next level. What's happening with the motor temperature? Is the dynamic of the situation changing with the motor temperature? And that has implications for the ambient temperature. If we have a map and we've seen this thing perform at that operating point 200 times already, and it has a certain characteristic, and all of a sudden the motor temperature is different, we know the ambient temperature has changed, or there's a damaged fan blade. And then we can amp it up and go all the way out to time. So now this intelligent device that's living in that mechanical room space, and it's seeing a certain characteristic every day, and after 5 years of learning and experiencing a continuously repeated trend of load, let's say, and flow behavior and valve position behavior, there are things we can do to be anticipatory and make the system perform better so that there isn't a lack of flow when that valve starts to open. So there's proactive things we can do, and we can also say, hey, all of a sudden, the load that usually occurs at that point in the morning isn't here, and we should put our hands up and say that the experience for the application has changed. And we create an equipment performance map in 2 dimensions for a pump that we expand now out to multiple dimensions, and we call that the fingerprint, the equipment performance map, that includes time, and it informs us greatly. Just from a pump level or a valve level, there are intelligent valves out there that do similar things today. Also, we've now got a multifunctional device that has a wealth of new data that we can leverage for predictive maintenance, condition-based maintenance, and other activities, including optimization of the plant itself. This is no different than the evolution that we've had in our telecommunications devices. When 25 years ago we had phones with wires and they hung on the wall, to now what we consider as our primary mobile device that is really a social media platform for our lifestyle also. So the functionality that we're getting out of these new intelligent devices, when properly leveraged, is increasingly powerful. So with that same approach to fingerprinting of a piece of equipment, we can do the same thing for all the devices in the chiller plant. That includes the chiller itself, the cooling towers, that's a 5-dimensional space. The chillers are a 9-dimensional space of performance mapping. And we can create these performance maps, allows us to start looking at combinations of equipment and what the impact of those combinations are in real time. So as any one piece of equipment starts to change, it affects the productivity of that equipment station. So if there are 3 pumps that you can operate in parallel and we find that one of them is starting to degrade, it will show that that combination of specific equipment is not ideal, and maybe we want to use the other 2 pieces of equipment a little bit longer before we bring in that one that's deficient in performance. It also allows us to say, how much capacity do we have now that we've got one of those 3 pieces of equipment in a degraded state? How much capacity do we have from that station? So when we talk about the design flow, the design day flow requirements of the cooling capacity that are required, we know what we can do. And in most cases, we can still do 100% capacity flow, even if one piece of equipment is degraded 20% in its performance. And then we expand the fingerprint wider and we look at the whole chiller plant. So the whole cooling system can have its own fingerprint. And what we do to optimize the plant is we take the combination of all those equipment performance maps, real-time digital data, and we take the combinations of ones that add up to the required load and wet bulb temperature of that given operating condition that the plant is experiencing at that time. They all include a power measurement, a power reading. We add up those powers for all those possible combinations, sort them, get the one that uses the least power, and that's the operating conditions that we're going to apply to the plant in terms of which pumps to run, which chillers to run, which cooling towers to run, what's the fan speed, what's the chilled water supply temperature, etc. So it's a whole new way of leveraging a digitalized capability to optimize the performance of the plant regardless of the condition of our equipment. What's the impact of this? This is one of the earlier projects that we did on a project site that's been well documented, and it had a dramatic impact on the PUE. It went from around 1.65, it was an all variable speed chiller plant to start, and then you can see the step down in performance when we implemented that optimization and that learning. So again, thinking about the impact of that PUE improvement on the global environment of our power supply, it's quite dramatic. In addition to that, it's able to diagnose and email out remedies that are required by the service staff at that facility to take action, or maybe a remote service supplier to go and improve the tightness of a belt on a fan if it's a cooling tower issue, or to clean a strainer on a pump, or check the refrigerants within a chiller. We're able to diagnose that and recommend the remedy. We're also able to predict the performance and measure the performance against the commitments that are made for that facility. So on a daily basis, the operator gets an email that tells them how well that plant performed yesterday, how well it should have performed based on our equipment performance maps, and if it gets outside of a tolerance of 3 to 5% of that predicted performance, we work on what the remedy is to get it back on track. So this is all about digital twins and being able to leverage the power of a digital twin with a data model as opposed to an equation model. A lot of optimizations today, the approach is all about equations, and equations are tough to modify. There are a lot of coefficients. There are a lot of changes in heat transfer coefficients on the equipment themselves, and that modeling can be very complex. So our approach has been digital-based. And when we started down this path approximately 6 years ago to do a purely digital machine learning environment without any equations, it was going to take us 99 years for the fastest commercially available computer to calculate the best combination for a 26-dimension chiller plant. That would be a 5-chiller plant. And with the advancements of some mathematical geniuses that we employed, and also the advancement of processor speeds and the availability of cloud learning, which we've taken some of our historical sites and the learnings we have on them and incorporated them, we're able to get that learning cycle down on a local processor to less than 2 minutes. So it's very adaptive, very able to respond to acute changes in condition, and also, more importantly, the one that's the real killer for us are the chronic changes. So something that goes undetected over the life of a plant, these small little changes in equipment performance are very difficult to detect. And we're now able to detect those with this learning process. One of the challenges with machine learning is machine learning bias. It can only learn from the operating points that it sees. So what we've integrated into this machine learning algorithm to eliminate that is a learning routine where we'll explore other operating conditions. So it's not only seeing its mapped operating conditions, but it looks at other operating conditions once a week to ensure that it's learning the full space and not just the operating space. And this is leveraged by our cloud learning. So multiple sites and the learning that we do in those learning modes at individual sites gets combined at the cloud, and there we get a lot more intelligence and directive in terms of how we want to adapt and change our control maps over time when we observe certain characteristics. So getting back to the cost of a chiller plant and what the implications this has for a chiller plant. When we design cooling systems for data centers, we're very concerned about resilience. We're very concerned about uptime and availability. This is a key criteria for every data center. But one of the reasons we're so concerned about that, and we go to N+1 designs and 2N designs, is we're unable to predict how much capacity do we actually have from our cooling system. With these digital maps, we're able to very accurately determine, given the next 3 months of trends that we know about and the last 3 months that we've observed and the weather patterns that we know are coming, maybe there's a change in season, we're able to actually predict the capacity that's available. And are we going to have a capacity challenge or not? And we'll be able to shift the amount of effort. If there's degradation on the cooling towers, we're able to shift the effort to the chillers and the pumping system. So it brings up new opportunities to have more resilience and availability through intelligence, as opposed to the brute force approach that we use with heavy carbon footprint N+1 and 2N designs, and gives us the opportunity for leveraging different combinations of equipment, such as 2 times 55% pumps and 3 times 40% chillers, and still have an operating sequence that will work in a very robust manner. So finally, to wrap up what we're suggesting in the design community practices, and we've started to do this, is by integrating intelligent equipment with new efficient designs that leverage feed-forward control and cognitive learning, we're able to provide the same availability, if not better, than our traditional approaches that are heavily brute force with the N+1 approach and other overcapacity measures that imply a lot of extra investment. So we're able to save on those investments through intelligence. We're actually excited to announce that we're launching a new platform for the data center community. The line is called the EverCool Platform, and it's got capabilities for all tier of uptime requirements, including tier 3. Very robust design, and if you want to learn more about it, we'll be presenting that at our booth, booth number 041, and we invite you to come by and learn more about our optimization and also our new data center automation platform. Thank you for your time, and I'll open the floor to any questions at this point. The question at the front, I'll repeat it, I believe was, does this integrate with BMS and other higher level DCMI type? Yes, it does. So the level of control, the relaying of data and information is seamless into those systems. There's complete read-write capability between the two platforms.
How do you account for redundancy? What happens if the unit malfunctions?
Could you repeat the question, please?
How do you account for redundancy? What happens if the unit malfunctions? Does something go wrong with the chiller plant and the Thomsen?
So the question is, how do we account for redundancy? The first point is that if there is a failure of equipment, we're able to predict it. So catastrophic failures that occur internally to the plant are detectable. If they're caused by external events like an airplane taking out the cooling towers, that's not predictable. So our first defensive measure is the predictability, and the second is to calculate the capacity that's going to be available. So if we do lose a cooling tower, we're able to shift the effort to the pumps and the chillers as opposed to one of 3 or 5 cooling towers, and tell the operator, do we have enough capacity for the load, yes or no? So the plant will continue to learn and adapt and optimize, first to meet the capacity requirements, and second for energy efficiency. Thank you very much for attending, and please enjoy the show, and we invite you to visit us at our booth 041. Have a great day.